Hi everyone, it's Aleem here. In this video, we're going to be looking at an introduction to optimization modeling in Excel using Solver. This video is based on the Winston and Albright Chapter 3 reading. In this chapter, we looked at spreadsheet optimization, which is probably one of the most powerful and flexible methods of quantitative analysis. In particular, what we're going to be looking at in this chapter is something called linear programming, and linear programming is useful for things like labor scheduling, inventory management, choosing where to advertise and how much to spend on advertising, product mix, bond trading. There are so many applications to it. I think it's a wonderful tool to learn how to use, so let's get right into it. By the end of this chapter, you should be able to identify different linear programming problems that you can solve. You should be able to model them in Excel, and you should be able to use Solver as well as Solver's sensitivity analysis to interpret the results of your linear programming model. Now, there is a lot of terminology that comes along with linear programming, so we are going to walk through some of that right now. I think it is really important that you take the time to learn these terms, to read about them, to make sure you understand them, so that when you're actually working on the models and you're trying to interpret the sensitivity reports, you aren't making silly mistakes. All optimization models have several common elements. There's something called a decision variable, and like we've seen in many of our other models, a decision variable is the thing you're allowed to choose, or the decision maker is allowed to choose. So for example, how many shirts do you order, how many of each product do you make, or whatever it is. Your objective, or your objective function, is the thing you're trying to optimize, and usually we're trying to maximize it or minimize it. And then a constraint is something that needs to be satisfied. You can have physical constraints, for example, the room only holds 20 people. You can have a logical constraint. If you're trying to lose weight, you can't eat negative calories, and don't tell me about celery. And you can have economic constraints. You might not have enough money, or you might only have a certain amount of money to spend. In searching for the values of the decision variable that optimize the objective, only the ones that satisfy all of the constraints are considered to be feasible or appropriate solutions. In Excel, you're going to see some different terminology. The decision variables, according to Excel, are called changing cells, and they are allowed to change. Okay, so in Excel, the changing cells are allowed to change freely. They're not allowed to contain formulas. Excel refers to the objective as the objective cell, and there can only be one objective cell. There can be many constraints, but there can only be one objective, and this could be your profit. It could be total cost, total distance traveled, right? If you're trying to minimize the distance on a trip. When the changing cells change, the objective cell should be linked to those changing cells, and it should change accordingly. One of the biggest mistakes I've seen students make is they forget to link their objective to the changing cells, and then they can't figure out why their model doesn't work. When you change the changing cells, your objective should change as well. Non-negativity is a very common constraint, which basically says that the changing cells have to be greater than 0, either non-zero or positive values. So for example, you can't eat negative calories, you can't produce a negative number of cars to save cost. Now there are two steps in the optimization process. One is where you develop the model itself, and that's called the model development step, and then 2 is the optimization step. In the model development step, you decide what the decision variables are, which constraints are required, and then how everything fits together. It's very useful at this stage to take a step back, think about your model, think about the inputs to your model, so that when you're setting it up, you can be efficient with it. In the past, prior to Excel, you might have developed an algebraic solution to look at how the variables fit together algebraically, but in Excel we can just set it up in Solver. And in fact, it's the model development step where most of your time and effort is going to go. The optimization step. To optimize means that you must systematically choose the values of the decision variables that make the objective as large if you're trying to maximize, or as small if you're trying to minimize as possible, while still meeting all of the constraints that you've specified. Any set of values that meets all of the constraints is said to be a feasible solution. And the set of all feasible solutions is called the feasible region. But there's also what's called an infeasible solution, and if you violate even one constraint, that solution is said to be infeasible and not permitted. The best feasible solution is called the optimal solution, and that's the one you're looking for. There are different methods in Excel to optimize. One is called GRG nonlinear, one is called evolutionary solver, but the one we're going to be using is a very simple one, and it's called, appropriately, the simplex method. Once you've optimized your solution, there is a third implicit step that does happen, and that's called sensitivity analysis. This is challenging because there's a lot of terminology you're going to see in the sensitivity reports, and they all kind of fit together. So the benefit to this is once you understand it, you'll understand it well. It might take you some time to see how all of the variables fit together, so you can make sense of all of this. Now typically, you would choose the most likely values of input variables, such as your unit costs or forecasted demands, or how many resources you actually have available to you. But in real life, you might not know exactly how much material you have. You might not know how many hours your employees can actually work. Maybe someone can work overtime. So in a realistic situation, all of your inputs could really change, and you need to see how your solution would change as a result of changing those inputs. What if you could run the machine for 1 extra hour? What would that do to your profit? What if you had an employee work an extra hour of overtime? How much would you be willing to pay them? In our first example, we're going to look at a two-variable product mix model. And this is a type of problem frequently encountered in business, where you've got to decide what to make and how much of each product to make. So if you've got one machine, but you could make multiple products on that machine, if those products take different amounts of time to manufacture, then you have to decide which product it makes sense to make the most of, while still maintaining a reasonable product mix, maybe subject to some market demands. In this example, you're going to see how to model the problem algebraically, then we'll plug it into Excel and solve it using Solver. As the final step, we'll walk through what's called a sensitivity analysis to answer some questions around what would happen if some of the inputs to the model changed. Let's take a look at example 3.1. Example 3.1 is called Assembling and Testing Computers. We're introduced to a company called PC Tech. They assemble and then test two different models of computers. They've got the Basic and the XP. The decision they're trying to make is how many of each model to assemble and test to maximize profit. Here's some background information. The monthly demand for Basics is 600 units, and the monthly demand for XPs is 1200 units. Now again, keeping this very simple, we're not talking about inventorying any of this. We want to produce up to the demand and no more. And we can't sell more than the monthly demand. This doesn't build in any extra advertising to maybe increase that demand or anything like that, but these are things we could look at through our sensitivity analysis. The selling price of a Basic is $300. The selling price of an XP is $450. Our assembly labor costs us $11 an hour, and our testing labor costs us $15 an hour. A Basic requires 5 hours of assembly and 1 hour of testing, and an XP takes us 6 hours of assembly and 2 hours of testing. So you can already see here it's going to take us twice as long to test an XP as it does to test a Basic, even though it doesn't take us that much longer to assemble an XP as compared to a Basic. Now the constraints, we only have 10,000 assembly hours, but we do have 3,000 testing hours. The one that limits our output is said to be a binding constraint, whereas the one that doesn't limit our output is said to have slack. Here's our big picture. Labor hours per unit, cost per labor hour, the cost of component parts or our direct material costs, as well as our selling price, our maximum sales, and our labor hours available are all inputs into the model. The top 4 boxes there, taken together, are used to calculate our unit margin or our contribution margin. The labor hours per unit, together with the number produced, give us our labor hours used, and the constraint there is the labor hours available. We can't use more hours than what we have available. Again, I realize in real life people could work overtime, but that's not what the number produced need to be less than or equal to maximum sales, and once again, in this example, we aren't considering any inventory. In an algebraic solution, you would first identify the decision variables. In this problem, it's actually fairly straightforward. It's the number of computers to produce, and you could label these x1 and x2. The next step is to write out expressions for the total net profit, as well as the constraints, and finally, because only non-negative amounts can be produced, you could set up explicit constraints as well to make sure that x's are greater than 0. For many years, in fact, linear programming was solved this way. But since 1990, and actually beyond, we now just plug this into Excel and solve it in Excel. Just to be clear, in this course, you are not responsible for solving an algebraic model. You can leave that to your math course. In a spreadsheet model, there are many ways to set up a linear programming spreadsheet. Every book you read is going to have their own convention or preferences for how you set this up. In this class, we're going to go through enough examples, so I hope you get a good idea of how how I expect to set these up. The common elements in all of your linear programming spreadsheets will be your inputs, your changing cells, your objective cell, and then your constraints. Inputs are all numerical inputs. Remember, you can't have a formula in an input, and our convention in this course is to color those blue. Typically, we try to put the inputs at the top left of our workbook. Again, that's just a convention. You don't have to set it up that way, but I do that so it's consistent with some of the other models we've looked at in this course. Sometimes we'll violate this convention when it fits more naturally to put an input somewhere else in the model, but generally we do try to keep them in the top left. Our decision variables, or our changing cells, typically are colored pink, and these are the things that we are allowed to change. The values in these cells must be allowed to vary freely, so there should not be any formulas in the changing cells. This slide mentions that to designate them clearly, the convention is to color them red. They call it red, but it really does look more pink. The objective cell. This is one cell, typically we shade it gray, and this is the cell that Solver is going to try to systematically vary the decision variables to either maximize or minimize. You have to link this cell either directly or indirectly to the changing cells through formulas. And then finally our constraints. Excel does not show the constraints directly on the spreadsheet. Instead, we have to specify them in Solver. So for example, you might have a set of constraints where B16 to C16 need to be less than or equal to B18 to C18. Now it's better to name your ranges so that when you're looking at it in Solver, it just makes a lot more sense. If I said B16 to C16 is less than B18 to C18, that's a lot harder to read than number to produce need to be less than or equal to maximum sales. Non-negativity. Normally, the decision variables, that is the variables in the changing cells, must be non-negative. However, if you want to constrain any other cells in your model to be non-negative, those you must specify explicitly. Let's take a look at how we're going to solve this problem. The complete solution involves 3 steps. In the model development stage, we're going to enter all of our inputs, we'll put in some trial values for the changing cells, and we'll set up our formulas relating these together. This stage is the most important because at this stage, we're going to actually make sure that everything ties together properly in our model. After the model is developed, we're going to move to the second stage, and this is where you invoke Solver. If you haven't done that yet, you're going to set it up by clicking on File, come down to Options, click on Add-ins, go to Go, choose Solver, make sure it's checked off, and then say OK. Once you launch Solver, at this point you formally designate the objective cell, and whether you're trying to maximize it, minimize it, or set it equal to something. You also identify the changing cells, the constraints, and you select options. Things like which type of approach you want to use to Solver, whether it's GRG nonlinear, evolutionary solver, or like we're going to do here, simplex LP. And then you just tell Excel, or Solver in this case, to find the optimal solution, and amazingly, it just does that. The third step is called sensitivity analysis, and it's at this step that we can see how the optimal solution would change, if at all, as a result of either changing your inputs or your constraints. And it is really important to understand the model really well before you can jump into the answer and sensitivity reports. But you are responsible for understanding Solver's answer and sensitivity reports. Now, one last thing to mention here is that in textbook land, typically you're going to get a problem, including a number of input values, and you're going to jump directly to a solution, and often we might not really step back to think about, well, where do those inputs actually come from? In the real world, it actually is the most difficult step to find out what the source of all of those inputs are. Who would you talk to? Where would you find out how many assembly hours you really had? What does it mean if I tell you we have 10,000 assembly hours? And by the way, an average employee works 2,000 hours per year. So if we've got 10,000 assembly hours, what we're really saying there is we've got 5 full-time employees for a whole year. Consider the source of the data, question the inputs as well as the model itself, think critically about whether or not the model actually makes sense, and then try to step back and understand the limitations of the model itself. With all of that in mind, let's take a look now at example 3-1, or our first product mix model. In this question, what we have is a company that's making two products, a computer called the Basic and a computer called the XP. The cost per labor hour at this company is $11, and the cost for testing is $15. To make a Basic is going to take us 5 hours for assembly, whereas to make an XP is going to take us 6 hours. For testing, it will take us 1 hour to test a Basic, whereas it takes us 2 hours to test an XP. Our cost of direct materials is $150 for the Basic and $225 for the XP, and then the selling price for each product is $300 and $450 respectively. Our unit margin is $80 for the Basic and $129 for the XP, and the way we calculate that is to take our revenue and subtract all of our costs. The formula for that is our selling price, which is $300, minus our cost, which is B8, and that's our labor hours required in assembly, times our cost per labor hour of $11, minus B9 times B4, and B4 is our cost per labor hours in our testing department, and from all of that we subtract our cost for direct materials, which was in cell B10. Now when we drag that across, we get $129 as our margin for the XP. Our decision variable is the number to produce. We want to know how many basics we should produce, and we want to know how many XPs we should produce, subject to the constraint that our maximum sales are 600 and 1200 units respectively, and that we have some constraints around assembly hours, and that's 10,000 hours, and testing hours, and that's 3,000 hours. Now when we type in 600 here, we already see that our assembly hours are what are limiting our output. We have enough testing hours, but our assembly hours are already over the number of hours we have available. So if it is our assembly hours that are limiting our output, one thing we would want to look at, even before running Solver, just so we can intuitively see what's going on here, is what is the contribution, or how much are we earning per hour in the assembly department? Because that's going to be how we favor which product we make. Now the Basics, we earn $80, and the XPs we earn $129 per unit. That doesn't tell us how much they're earning per hour in the assembly department. And to calculate that, we divide 80 by 5, and we see we earn $16 an hour here, and when we drag this across, we make $22 an hour on the XP. Let me just increase my decimals so we can see exactly what we're dealing with here. $16 and $21.50. Now, when we run Solver, we'll click on Data and click on Solver. Just to very quickly show you here as well, to install Solver, click on File, come down to Options, choose Add-ins, click on Go, and then make sure the Solver add-in is checked off and say OK. You'll see that then under the Data ribbon, and here's Solver. When we open Solver, we've got our total profit up at the top, and that's our objective. That's this cell down over here. We want to maximize that, so make sure you have max checked by changing variable cells, and that's the number to produce. Now you can do this in a number of ways. You can either enter the cell reference here, or you can click the little arrow here and highlight the number to produce. Now you'll notice here that this says B16 to C16, but because we've already named our ranges, it will pick that up once I exit out of here as number to produce. Subject to the constraints, hours used need to be less than or equal to hours available, and the number to produce need to be less than or equal to our maximum sales. Make unconstrained variables non-negative, use simplex LP, and then click on Solve. When you do that, you get this screen. Our Solver results tell us that Solver found a solution and that all constraints and optimality conditions are satisfied. It's at this screen you could choose to have the answer report, the sensitivity report, or the limits report. You can generate as many of these as you want, and then say OK. Now I won't say OK here because I've already done that. And in our sensitivity report, here's what we see. I want you to notice that at the top, we've got our number to produce for Basic and our number to produce for XP, and our constraints at the bottom refer to the labor hours of availability for assembly and the labor hours of availability for testing. The allowable increase indicates how much the coefficient of profit margin, which is currently sitting at $80, could change before the product mix would change. So here what this output is telling us And if you look at the final value column, you'll see what I'm talking about. It says we should make 560 basics and all 1200 that we can sell of XP. And if we do that, we're going to make as much money as possible. What this is telling us is that $80 coefficient could increase by $27.50 or decrease by as much as $80. That is, it could be zero. And if that were the case, nothing would change about the number to produce of basic or XP. Now, outside of that range, our product mix would change. So if the coefficient, that is how much money we make, of basics stays between $0 all the way up to $107.50, then the optimal number of basics to XPs won't change. Outside of the range, they might change. One nice thing about the way I've set this up is you can see the contribution margin per our constrained resource in this case, which is $16 and $21.50 respectively, and I could show you a couple of quick things. If I was to increase my contribution on the basic, and again going back to the sensitivity report, the allowable increase was $27.50. So if I was to increase this by more than $27.50, we would see that this contribution margin per hour in our assembly department would then exceed that for the basic, and mathematically we would favor producing the basic over the XP. So let me show you this. Let me add $25 here first, so we'll go to $325. And now we're at $21, we're not there yet. Let me go to $27.50, so $327, oops. So $327.50. And now we're at exactly that crossover point where they're equal to each other. At $328, we're now past that point. So now it makes more sense to make the basics over the XP. Let's return that back to $300. Similarly, for the XP, I had an allowable decrease of $33. So let's subtract $32 from the $450 so we can see what happens here. And if I subtract $32, we see that we're not quite at 16 yet. When I subtract $33, we can see that we're exactly at $16 for each product. And then finally, if I were to subtract anything more than 33, let's say 34, we're now at that point where it makes sense again to make the basic over the XP. So I just wanted to show you very quickly some of the stuff going on in the background here. You don't really have to have a full understanding of the contribution margin per constraint to understand linear programming, but I think it certainly helps to know what's going on in the background, so you're not just relying on Excel to do this blindly. The reduced cost, which we see in the second column, shows you how much the coefficient of a decision variable that's either at 0 or at its upper bound must change before the variable changes. Now that sounds a little bit confusing, but it's easier than you think. In this case here, we're making as many XPs as we can sell. 1200 was limited by the number of XPs we could sell, which was also 1200. The fact that we're seeing a reduced cost here is because we're at that upper constraint or upper bound of the number that we could sell. I also want you to notice here that that reduced cost of 33 is equal to the allowable decrease of the coefficient for XPs. That is, the $129 could decrease by $33 or by up to $33 before the number of units would change. Currently, we're producing as many XPs as are demanded, which is 1200, and this won't change unless the profit margin of XPs decreases by $33. Again, try this. Once you read this, pause the video, go give this a try. Starting with the original inputs, change the selling price for XPs to $420, which is a change of less than $33, and you should see no change if you rerun Solver. But now try changing it to $410, which is a change greater than $33, and now you're going to see that we'll make fewer than 1200 XPs. Now we'll take a look at the constraints area of the sensitivity report, and that's the bottom part of it. First of all, before we even talk about the shadow price, let's take a look at how much of each of the constraints we're using. If we look at assembly hours, we're using 10,000 hours out of the 10,000 hours available. If we look at the number of hours we're using in our testing department, we're only using 2,960 out of a possible 3,000. So there we have slack of 40 hours. Our shadow price shows up when we have a binding constraint, which in this case we do with respect to assembly hours. The shadow price indicates the change in the objective, so how much profit would increase or decrease, when you change the constraint by 1 hour, or 1 unit. In this case, we're talking about hours. So said another way, if we had 1 more labor hour available to us, what would happen to profit? Well, if assembly labor went from 10,000 hours to 10,001 hours, profit will increase by $16. And you can think through why that actually works in the model. Think about it for a second here. We earn $80 for every basic we sell, and it takes 5 assembly hours to make a basic. Excel doesn't know we're talking about manufacturing computers here. It doesn't know that you can't make 1/5 of a computer. So here's the math that's going on behind the scenes. If we increased our number of assembly hours by 1, with that 1 hour, we could produce 1/5 of a computer, or we could assemble 1/5 of a computer. Because there is no limit in their testing department, we've still got 40 hours available to us. That's not going to limit our output here. So as far as Excel is concerned, we're going to make 1/5 of a computer, or 1/5 of the profit that we would generate from selling 1 more computer. The profit we make selling 1 computer was $80, and 1/5 of that is 16. Now the shadow price only is valid within a certain range. You'll notice here that we've got an allowable increase of 200 and an allowable decrease of 2,800. And what that's telling you is that $16 shadow price per hour is only valid between 7,200 hours and as high as 10,200 hours. Now you can think about that logically for just a second here. If I gave you an extra 200 assembly hours, 200 divided by 5 would allow you to produce 40 extra units. Those 40 units would sell for $80 each. 40 times 80 is $3,200. Now if you did the math the other way, the allowable increase of 200 hours times $16 per hour is also $3,200. If you take a look at the labor hours though for the testing department, this is a little bit more confusing. I want you to notice the 1 times 10 to the 30. That's the allowable increase on the 3,000 hour constraint. Now I want you to think about what that actually means. That 3,000 hours technically could increase to infinity with no impact to our solution. Right now we're not even using 3,000 hours, so even if I had 30,000 hours, 10 times as many, it's not like we could make even 1 more of these computers. We wouldn't have anything to test at all. Given our constraints in the assembly department, we're only able to test for 2,960 hours. So even if I had 30,000 hours, it wouldn't impact my solution or my objective. And that's why the allowable increase for the 3,000 is 1 times 10 to the 30, or basically it's saying infinity. In contrast, the allowable decrease for the 3,000 is 40 hours, and that's because we're currently using 2,960 hours. If we dropped that constraint by more than 40 hours, that would take that constraint below 2,960, and now our testing department would limit our output. Now there are some things you need to be aware of with your constraints. One thing is called infeasibility, and the other is called unboundedness. Now these are quite different from each other, but I find that for whatever reason students do tend to confuse these, so let's walk through what each of them mean. Infeasibility occurs when there is no feasible solution, and generally this is when you've typed in an input either incorrectly or you've set your inequality in the wrong direction. But all you're really saying is you've given solver too many constraints and it cannot find a solution amidst all of those constraints you have specified. Unboundedness is the opposite situation. Here you haven't put in enough constraints, and what Excel is telling you is it can make your objective as big or as small as it wants to. I also find it kind of creepy that Excel is talking about wanting to do much of anything, but anyway, the point here is that if you don't specify enough constraints, then Excel is just going to get very confused and say it is unable to converge, or the objective cell will not converge. Now these are quite different. It is quite possible for a reasonable model to have no feasible solutions. And the only way to solve it then is to get rid of some of your constraints. Unboundedness is a little bit different. There is no way a realistic model can be unbounded. If you get this message, you have made a mistake. You've probably entered an input incorrectly, or you've omitted one or more constraints, or there's a logical error in your model, so you'll need to take a step back to think about what it is you're actually doing. If you have the Winston and Albright reading, take a look at section 3.4, Sensitivity Analysis. This will be tested on our exam. I really encourage you guys to read this. I think they've done a great job of walking through it. They have developed a product called Solver Table. You are not responsible for it because you won't have access to that product in the real world. It was developed by the authors of this book.